Yes, we are back live. Excellent. I cannot believe it is already the 12th. Just cross this out right here. That is insane to me. Oh, goodness gracious. There's so many people that I know that are quarantining as a result of a number of different things. Most of my family is quarantining. I'm apparently the only one that is vaccinated. They actually changed the guidelines once again. I don't know if you guys know that, but if you are fully vaccinated, New Jersey changed the guidelines where it's either if you're fully vaccinated or if you've had COVID and recovered within the last 3 months, then you don't have to quarantine from like out of state travel or some junk like that. They just changed that on April 5th, which is like, cool. All right. Whatever. They just keep changing things, but I don't know. The numbers are still consistent and we're still here. So here we go. When is that change happening? Do you know when they're going to change it where you guys have to stay till like 2 o'clock? Oh, okay. So we got 2 weeks. Okay, that makes sense. That does make sense, yeah. Because if they have to quarantine and whatnot, yeah. So April 26th then. I mean, I'll double check that, of course, but I don't know. All my email is a mess right now. I had to delete like a bunch of junk emails, but I got to go through some stuff. Anyway, the marking period, yes, came to an end on April 1st, but grades are not due until April 15th. I had posted something in Google Classroom right at the beginning of spring break where I had said, attention, teachers are required to submit grades before April 15th, and we're currently on spring break. This translates to you having some extra time to turn some things in. Now, I say that for me, that doesn't necessarily translate to every other teacher. I'm saying that mainly for me. I am in no way done grading things, so please do not worry if Genesis isn't updated quickly. Email me if you have any questions, but keep in mind, emails won't be checked frequently in the next week. And they weren't. They definitely were not. And here we are back once again. So we got the next 2 weeks with the 60-minute class periods, and then we should be transitioning to like the 84-minute class periods, which they still haven't given us clear direction on those 84 minutes, but whatever, that's where we're at. Okay. My goal for today is to introduce the next step in paths and circuits. Before break, I spent a lot of time talking about Euler paths and circuits. The idea of hitting every single edge exactly once and being able to complete either a path or a circuit being right back where you started, in that Euler fashion. Now, I would like to introduce to you the next step, which is going to be called Hamilton paths and circuits. Now, in my opinion, Hamilton paths and circuits have a bit more calculations potentially to be done as a result, but they are just equally as nice. But I'll get into those details. They visually feel a bit nicer, but that's my opinion as well. Yes, in case I forget, for those of you in the live chat, I almost forgot. It's been 2 weeks I haven't done it. And if you have not left a comment in the chat, please make sure that you do so. That would be fantastic. So I can take that updated attendance. Please leave that comment in the chat. In the meantime, if you do not already have them out, I'm going to need those notebooks out and open. Let's see here. Now, I'm sitting over here at my desk. Oh, and I got some emails back already from people. Interesting. I should get out of that. But I will have the chat open on my phone right here. There they are. As I get into this stuff. I do have a PDF for you guys. For those of you that are here, I have physical copies of the PDF. Oh, I get the hiccups. But we'll deal with that when the time is appropriate. Let's see here. Click, click, and click. Haha, click. Excelente. Today is the 12th That is unbelievable. 75% of the school year done. We are almost there. This is Hamilton paths / circuits. We're still dealing with paths and circuits. I'm not leaving them alone. We are sticking with them. Obviously, Euler is one type of path and circuit that we could potentially go. Again, Euler was the idea that you had to hit every single edge, every single connection exactly once. You could think of it like the Coensberg bridge problem, where you had to cross every bridge exactly once. For Euler paths and circuits, sometimes it was not possible to complete a path or a circuit depending on the degree of the vertices. But again, we're going to review that stuff another time. Today, I want to talk mainly about Hamilton paths and circuits. So first of all, a Hamilton path. A Hamilton path, I'll just abbreviate it for now as an H path. A Hamilton path is where instead of visiting every single edge exactly once, you visit each vertex once and only once. You visit each vertex once and only once. So instead of thinking about crossing every bridge, you have to visit every landmass once and only once. It's just changing a perspective on it. You're trying to hit every single destination, every single vertex, once and only once. You might cross over multiple, not necessarily multiple paths, multiple lines, because of that visiting the vertex. You can only go into the vertex once and then leave the vertex once. Whereas a Hamilton circuit is basically the same as a path, same as path, but start and end at the same vertex. The general idea of a circuit, having a complete circuit, is basically starting and ending in the same exact location. A path is just, I hit every vertex exactly once. But a circuit may be more helpful in the sense that you are returning back where you started. Now, before we left for break, I did draw something like I'm about to draw, and kind of talk about creating like multi-pointed stars and things of that nature. But you could think of a Hamilton path or circuit like a map. And this map may look something like this, where I could reduce it to a bunch of destinations, a bunch of vertices, and I only have 5 up here right now. And I could name these things anything I want. Let's just say, and I don't know the exact distances here, but I am going to label these after places that we can recognize. There is Barnegat right there. There is Stafford. There is Little Egg. Let's say up here is Tom's River. And over here is Lacey. Just naming a bunch of places that we recognize. Now, this is obviously not drawn to scale. The exact locations of these vertices is not accurate, clearly. But if I were to describe each vertex as a destination and make a connection, I could say, well, yeah, there's a direct connection between Barnegat and Tom's River. I could drive directly from Barnegat to Tom's River. Or I could drive directly from Barnegat to Lacey, or Barnegat to Little Egg, or Barnegat to Stafford, depending on where my destination actually was. You could say the exact same thing for Stafford. You could say, well, yeah, Stafford, you could drive to Barnegat, or you could drive to Little Egg, or you could drive to Lacey, or you could drive to Tom's River. And you can see the shape hopefully beginning to take form. Same thing with Little Egg. Well, I've already gone to Stafford and Barnegat, but from Little Egg, I could also drive straight to Lacey, or I could drive straight to Tom's River. And then the only other connection that I haven't made is the Lacey to Tom's River connection. Now, every single location here has a direct connection to the other one. The distances are going to vary clearly. You know, Barnegat to Stafford is obviously a lot shorter of a distance than it is from Barnegat to Tom's River. And we would usually indicate that by a numerical value, but that's besides the point. I'm just trying to get the idea of, okay, if I start in Barnegat, I can make a Hamilton path. I can make a Hamilton path by going from Barnegat to Stafford to Little Egg to Lacey to Tom's River. Boom, there's a Hamilton path. I just have to visit every vertex once and only once. Whereas I could also do a Hamilton circuit if I did, and then this is, I'm going to go in a weird direction here. Here's a Hamilton circuit where I could go from Barnegat to Little Egg, to Tom's River, to Stafford, to Lacey, all the way back to Barnegat. That's a weird direction that I went, but it still counts as a circuit because I ended up back exactly where I started. Again, the huge difference between Euler paths and circuits and Hamilton paths and circuits is that in Euler, you have to hit every edge, and for Hamilton, you have to hit every vertex. That's all that it really, that's the huge distinction that it comes down to. So, let me try something right here. First of all, how many, I don't know if you can count it or if you can take like a wild guess. How many connections do we have up here? How many connections did I make?
I got
11? I'm going to go outer and then inner. I'll do it at the same time. So it's like a 1, 2, 3, 4, 5. Those are the outer, right? And then 1, 2, 3, 4, 5. Did I miss one? 1, 2, 3, 4, 5. No, there's 10, right? Yeah, there's 10 connections that you can make. 10 connections that you can make. Which is weird. There is sort of a mathematical way of talking about that. I just want to think about that for a second. But then, how many different ways I could actually go through this? Like, for example, I started in Barnegat, but I could have started in any 5 of them, right? I could have started in any 5 of them. But if I start in Barnegat, I have 1, 2, 3, 4 choices. 4 choices to go to. And then once I choose one, well, I'm not going to go back to Barnegat right away. And now I have 3 choices to choose from. I can go to Tom's River. Then I have 2 choices to choose from. I can go to Little Egg. And now I have 1 choice to choose from, Stafford. There are going to be mathematical principles coming up in this thing. I just want, again, this is an introduction. I just want you guys to start thinking about the different ways that you could technically go through these things. Side note question. I did not teach anybody here geometry, clearly, because I haven't taught geometry in like 12 years. Did you ever do something called the handshake problem? No? Somebody once told me that in geometry you did the handshake problem. It's like, for example, let's just say there's like, 20 people in the class, right? And and everybody has to shake hands with everybody, right? Let's pretend there's no COVID, okay? But if everybody has to shake hands with everybody, well, me as person number 1, I'm going to shake everybody's hand. But then person number 2 doesn't have to shake my hand, but they're going to shake everyone else's hand. So I might shake 20 hands, And then person number 2 has already shook my hand, so they'll shake 19 more. And then person 3 has already shook the first 2, so they'll shake 18 more. It's a similar concept. It's a weird concept, but I like it. Again, we'll get into the math of that eventually. I don't know. I thought you guys had done like the handshake problem. I guess not. Whatever, clearly. But you probably would have remembered that. It's weird talking about that and being in COVID. Where's my paper? There's my paper. With a Hamilton path and circuit, the general idea is that you start off with a certain number of vertices, certain number of destinations, and you make the connections between them. Now, I'm actually going to draw this one out for the sake of argument, but let's see. I go here, and then here, and then here, and then here, and then here. Right, but then I never made the connection here. Interesting. When's the last time any of you were at an airport? Never? Really? 2 years ago? Yeah. It's been a while for a lot of people. It's been a while. Again, full disclosure, I was just on an airplane last week. Yay. Cool. Good for me. But I'm vaccinated, so ha 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 ha. I don't care. Anyway, it's very interesting to think, like, yeah, there's a connection between what's the closest airport? Atlantic City? Yeah. Atlantic City to Philly. And then Atlantic City to Newark. I don't know why there would be a connection there. But then, like, Atlantic City doesn't fly everywhere. You know what I'm saying? Like, Atlantic City might not have a direct flight to, like, I don't know, Cheyenne, Wyoming or some junk like that. I don't know. Might not have a direct flight. So you may have to take, like, a connecting flight. The idea of Hamilton paths and circuits runs with the assumption that you can potentially fly or drive or walk from one vertex to the next. But in real life, there may not be a direct connection between two vertices. There may not be. I don't know. It really depends. I've never had to take a connecting flight. Have you ever had to take a connecting flight? Yeah, I've heard they're weird. I'll tell you a quick story about flying. It's not my story, though. I have a sister who lives in North Carolina. Okay. I can't remember the name of the town now because she's moved around so much. She married a Marine and he was transferred every 3 years, blah, 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 blah. Long story short, she's in North Carolina. My parents go down to visit her, right? So my mom looks up all the stuff online, books the tickets. They go to Atlantic City for the airport. They fly down. And the airport is in a place in North Carolina. Once I say this, you'll know where the story's going. But the airport is in Jacksonville, North Carolina. Okay? You know where the story is going? They ended up in Jacksonville, Florida. Yeah. They didn't realize that till they landed. My mom was so embarrassed. My dad was so angry. And it was like literally my sister's on the phone with people at the airport trying to explain to them like what happened. But like Jacksonville, North Carolina, Jacksonville, Florida. So sad. Anyway, that story is from like 8 years ago. I have too many airport stories. Back to this. Yeah. So with a Hamilton path and circuit, typically we don't label them with, town names. I mean, we could if we wanted to. But I'm going to label these with letters A, B, C, and D. Now, again, I haven't labeled any of these with the numerical value. Ooh, guess it turned into a Florida vacation. No, Sydney, it didn't. They flew home and they decided to not go on vacation. It was so sad. Anyway, I have another story. My parents I can't remember where they were going, but my parents recently got a tiny Chihuahua dog who is the bane of my existence. You guys seen Chihuahua dogs? Disgusting. Anyway, I drive my parents to the airport, drive them to the airport. They have the Chihuahua dog in one of those, what are they called? Carrying boxes? What do they call them? Like a crate. Thank you. Like a dog crate or whatever. Right. So I'm driving to the airport and I'm like, So you're allowed to take that dog crate on the plane, Mom? And she's like, yeah, I'm allowed to. Yeah, of course I am. The dog's in a crate. Why not? I'm like, well, okay. She's like, yeah, I brought, I've taken the dog on flights before. I'm like, yeah, well, the last time you took the dog, she was a puppy. She's not a puppy anymore. It's a Chihuahua, but it's a fat Chihuahua. Like my parent. Oh my gosh. Anyway, so they get to the airport. I drop them off. I'm like, all right, see you guys. I'm driving back. They dropped them off in Philadelphia. I drive them back. I'm driving back over the bridge, and I get a phone call from my sister. You need to turn around right now and get the dog. And I'm like, what? And she's like, yeah, they will not let the dog on the plane. Mom is in the airport crying. Like, they had the wrong size crate. It's a mess. You have to go back and get the dog. And I'm like, I'm not taking care of this dog. Like, are you kidding me? It was this whole mess. I had to bring the dog to a secondary location for so the dog could actually go on vacation. Such a mess. I hate the airport so much. But anyway, back to this. Sorry, Sydney's leaving emojis in the chat right now. Y'all can't see it. Anyway, now with 4 destinations right here, we could pick any destination to start with. I'm going to start with destination A, and I am going to write some of these out. So I would ask that you do copy these down to the notes as well. But clearly, the most straightforward way that I could go around this Hamilton circuit is this direction: A, B, C, D, A, where I start in A and I end in A. Yes. But that is not the only direction I could go on. I could also go A, C, I don't know, D, B, A, or some junk like that. I could also go A, B, D, C, A. I could go A, C, B, D, A. I could go A, D, C, B, A. Or I could go A, D, B, C, A. Yep. Those are, right there, those are the 6 possible directions that I could go in if I started at A. If I started at A. In order to complete that Hamilton circuit. Now, obviously, you don't have to start at A. You could start anywhere you want. I'm not going to write all of them out. But if there are 6 possible circuits that you could go on starting at A, then there should be 6 for starting at B, and 6 for starting at C, and 6 for starting at D. There are 24 possible Hamilton circuits with 4 vertices. And of course, that's assuming that there's a connection between all of them. There's 24 possible Hamilton circuits with 4 vertices. Now, I listed these out in a systematic way. Sometimes it is not in your best interest to actually list them out. Like, for example, now, by the way, I'm going to show you something, but I'm not going to expect you to draw it. I'm going to show you something, but you do not have to draw this. I just want to emphasize this. If I showed you this picture right here, clearly this would be insane to have to list out all of the possible Hamilton circuits for this particular image right here. Why would anyone in their right mind actually do that? No, you don't have to. We have computers for that nowadays. But we are going to eventually have to traverse our way through something like this. It's kind of nice. So, let me make sure I get to the right thing here. Cool. All right. I'm going to give you guys something to kind of show you where direction we're kind of going in here. Or do I want to give you, or do I want to draw that first? No, I want to draw it first. Yes, I'm going to draw this one. Okay. I want you to draw the following. And we're going to do this one together. I'm drawing it directly off of a worksheet. that I am going to give you guys. Now, there's not going to be a direct connection between every, well, no, technically there is a direct connection between all the vertices, but I am going to label these with numbers. And I'm going to ask that you do the same as well. Let me zoom in on that. I want to make sure I get the numbers right. Yes. Yes, I believe I have right there. Those are the numbers right there. Okay, that's a 10 right there. There we go. Let's pretend that this is a town with 4 destinations in this town. I don't know what kind of town would only have 4 destinations. Maybe this is the route of somebody delivering things to vending machines or restaurants or some junk like that. I don't know. But this is the route throughout the town. There is a direct connection between every vertice. So, for example, and I'm going to label these A, B, C, D. A, B, C, D. There is a direct connection between every vertice. But the connections are not all created equal. They are not all created equal. From A, if you start at A, you could go to any of the letters. You can go to B, you can go to C, you can go to D. But depending on which one you choose, it's going to take a certain amount of time to get there, or a certain distance. These numbers could be represented as time, or they could be represented as miles, or whatever. Doesn't matter. Money, maybe it cost them $20 to go from A to B. I don't know. There's a toll booth on the Parkway between Barnegat and Waretown. Do you remember how much that costs? It's like $1.90 now, right? When I was a kid, it was 35 cents. But they had, I believe you only had to pay going one direction. Yeah, I think you only had to pay going south, something like that. But it was 35 cents. 35 cents. But I'm just saying that if you travel from Barnegat to Waretown, you pay nothing. But if you travel from Waretown to Barnegat, you have to pay a toll on the way, So again, depending on the direction, even in some cases, you have to pay money. So the question becomes, how can we optimize? How can we optimize this route? Let's just say that these all represent like time. This is the time it takes to travel from one destination to the next. How do we optimize in order to spend the least amount of time on this route? There's a whole bunch of different ways that we can go about this. There's a whole bunch of different methods that we can use in order to get this thing done. Let me talk about something right here. Just for instance, I'm going to take a little side note. A, B, C, D, A. Zoom out. A, B, C, D, A. Probably the simplest route that you could take. If I were to go on this route, I would be spending 20 minutes, an additional 15 minutes, an additional 50 minutes, and then an additional 30 minutes to get back where I started. If I were to add all of those up, 20 and 15 make 35, 35 and 50, what does that make? Is it 115? Altogether? Oh, yes, sorry. You were in my head, I was trying to add 35 and 50, and you're like, 115. I'm like,
I just averaged the 30 and 20 and then 50, 50, 50.
oh, no, absolutely. Now, check this out. Check this out. This is insane. Look at that. Look what I just did. It's a little side note because I just wanted to show you guys. Check this out. This is insane. Red. I could start at A, B, C, D, A. That's the route that I took. But if I go this one, B, C, D, A, B, B, C, D, A, B. What do you notice about that? What do you notice about B, C, D, A, B versus the first one? It's the same thing. It's exactly the same thing. I just shifted over the letters. It's exactly the same thing. It's the same route. You're just shifting it over. Equals 115 as well. They are the same route, just shifted over. They're the same route, just shifted over. You could state this route as A, B, C, D, A. A, B, C, D, A. Or you could state it as B, C, D, A, B. Or you could state it as C, D, A, B, C. Or you could state it as D, A, B, C, D. All four of these routes are exactly the same. They're exactly the same. The reason why I'm making such a huge stinking deal about that is because of what we did over here. There were 24 possible Hamilton circuits, 24 possible. But if we want to optimize the route traveled, all we have to do is check 6 of them. That's all we have to do. Because if we check this one, the A, B, C, D, A, we are automatically checking all 4 of these because they are technically the same route. What we're about to do, this is what we are literally about to do. I want to check all 6 of those routes. And if we check all 6 of those routes, then we would have checked technically every single route to find the optimal route. We've already checked one. Let's check the rest. We need to figure out the shortest distance, the least amount of time traveled in order to optimize this route. Let's see here. Come on, paper, do your thing. Ooh, where'd I put you? There you go. No, I didn't put you there. Did I throw you? I didn't throw you. Oh, I left you up there. Sorry, I'm looking for my marker. Usually I throw things. There we go. So, we have already checked A, B, C, D, A. I'm just going to copy these down from before. Then we also have to check A, B, D, C, A. A, B, D, C, A. Yes, we're going to check that in a moment. Now, may seem weird just to switch up those 2 letters, but if we go back to this route, I believe we should be getting a different number. A, B, D, C, A. This is the second route. What does that add up to? That one's probably a little easier to add up in your head. Yeah, it's 150. If we go that route, where instead of going B, C, D, we go B, D, A, by changing that one little letter, by changing that one connection, we go from 115 up to 150. Holy crap. Again, if this were representing minutes, if this were representing minutes, that is an additional 35 minutes of traveling. Those 35 minutes of traveling are 35 minutes of gasoline that you're spending. Those 35 minutes of traveling are 35 extra minutes that the company is going to have to pay you for making those deliveries. We have to optimize this route. I would also like to check, let's see, A, C, B, D, A. A, C, B, D, A. I'm going to bring the map back in a moment. If I go A, C, B, D, A, again, I can draw this up here. A, C, B, D, A. What is that? 125? 125. Now, better, but not as good as the first one. Not as good as the first one. That's 125 if you add those up. Let's see. 125. A, C, D, B, A. Switching that up again because it's a different route that we're doing right there. A, C, D, B, A. Let's see, I won't draw on the board again, but A, C, D, it's 120 so far. B, A, that's 150, you know. Got two more to check. A, D, B, C, A. A, D, B, C, A. A, C, B, D, A. Is that 125 again? Interesting. And then finally, A, D, C, B, A. A, D, C, B, A. If I were to do that, A, D, what did I say, C? Yeah, I think I said C. C, yeah. A, D, C, B, A. Oh, interesting. 115. Huh. How come we keep getting the same numbers? What do you mean? Explain more. Like we got 115 for the first one and 115 for the last one, right? I agree. I totally agree. Do you know why? Move this over for. Yes. Same numbers. Use the word flip. I'm going to use a slightly different word. Ready? You said it was similar. I'm going to tell you it's the exact same path, except reversed. It's literally just reversed. Think about it. Instead of going A, B, C, D, A, you're going A, D, C, B, A. It's the same path, just flipped. Like you said, reversed. It's insane. Now, we're only doing this with 4 vertices. We're only doing this with 4 vertices. Do you guys know what a traveling salesman is? Do you know what a traveling salesman is? Yeah. Back in the day, they were much more common. Back in the day, they were way much more common. In fact, one of the more common stereotypes was the traveling vacuum salesman, where they would try to go to the house during the work day because the husband wasn't home. They would knock on the door. There'd be the wife. They'd kind of not barge themselves in, but they would kind of like get into the house and they'd be like, oh, let me show you this brand new vacuum cleaner. And they throw a bunch of dirt on the ground and the wife would be like, what the heck are you doing? And he's like, well, let me show you the brand new vacuum cleaner, you know, and then try to get her to buy one without the husband knowing. They were snake oil salesmen. It was a really bad situation. But anyway, traveling salesmen used to be very common back in the day. Obviously, if you're traveling from city to city, you need to optimize. optimize traveling distance, optimize traveling expenses, optimize traveling time. It depends on what you want to optimize. What is it that you're trying to minimize? How much you're spending, the time that you're on the road. It really depends. Now, we're only doing 4 destinations here. We're only doing 4 destinations here where you have to hit every vertex exactly once. But as I said before, what if it were something like this, where you had to hit 7 destinations and you had to optimize what the heck it was that you were supposed to do? It would take forever to list out every single possible conceivable outcome. I mean, it wouldn't be impossible. It would just be tedious. And I am not going to expect you to do something like that where you have to list out every single one. No, you don't have to. Let me give you a slight definition here. A slight definition here. What we just did in listing out all of these things is a strategy, or what they call a traveling salesman strategy. So this is traveling salesman strat 1. There are technically going to be 4 strategies that I eventually introduce to you, but this is traveling salesman strategy number 1. And it is called brute force. It is called brute force. You list out all possible Hamilton circuits. You list out all possible Hamilton circuits. I mean, there's definitely a pro and a con to the brute force method, the brute force strategy. There's a pro and a con to it. Pro, you will definitely get the optimal route. You will definitely get the optimal route. Absolutely. That's a pro. Con, well, if you had a lot of vertices, like 6 or 7 or 8 or 9 vertices, that might take forever. It might take forever. We only had to list out 6 of them. And those 6 technically kept repeating because of the reverse nature of it all. Not only that, again, I could shift this over and get the remaining routes that I wanted to, depending on any destination I wanted to go to. But again, if this was like, if you were traveling across country, you would have to figure out an optimal route. I took this class in college. It was called Operations Research. And Operations Research was solely about optimizing situations. Optimizing the amount of money being spent, optimizing the distance being traveled. It's all about money. For example, I talked about the Parkway. Talked about the Parkway. Now, when you travel on any major highway or parkway or something along those lines, there are toll booths for the most part. And especially on like the turnpike, if you've ever driven on the turnpike, they get a lot more toll booths than we do. But anyway, if you are the person in charge of scheduling when people would work the toll booth, you are responsible for saving the company the most amount of money. Because if you put someone to work, you are paying them to work. And if they are working, then they are collecting money from the cars going through. You want the cars to go through in a swift fashion because the more cars that go through, the more money that you take in. But you don't want to schedule every single toll booth worker from 8 a.m. to 8 p.m. Why don't you? Why don't you just schedule? Say again? Oh yeah, they get tired. What else? What else do you know about driving on turnpikes and parkways at certain times of the day? You've heard of rush hour? Rush hour. Think about that. People going to work at like 9 o'clock, people coming home from work at 5 p.m. You're not going to have every toll booth worker working at 1 in the afternoon, because if everybody's working at 1 in the afternoon, there's barely anybody on the road. And you're paying those people to basically do nothing. You have to figure out how to optimally schedule your employees so that, number one, you have people working 24 hours a day, because the turnpike doesn't close. You have to have toll booth workers 24 hours a day. But at the same time, you can't schedule everybody for the same time. You have to account for rush hour. You have to account for lull periods. Ugh. A buddy of mine, after high school, worked on the Garden State Parkway, and he had the night shift where he worked like 10 p.m. to like 6 a.m. or some junk like that. And he said that during those hours was when you had the craziest people going through the parkway, the craziest people on the parkway, traveling like 90 miles an hour, celebrities going through in limousines, people coming home from like Seaside or coming home from Atlantic City. It was insane, he said. Oh, gosh. He only lasted in that job for about a year. But whichever, it works. Actually, this is going to sound weird, but that friend who worked at the toll booth was Derek. Derek is like, he's in every single story I tell, almost. I wonder how he's doing. Anyway, I digress. Let me give you this worksheet real quick. I want to show you something. So for those of you online right now, boom, I'm posting this brute force practice worksheet. I want to talk about a few things. And for those of you that are here, obviously, oh no, my microphone. I have this worksheet for you. Oh, I got hiccups. Oh, I got the hiccups. Come here. Here we go. Oh, who's in trouble? It's Marcus room. Hey, good, how are you? It was okay, it was good. Yeah. Oh, right. Oh goodness. I'm probably good most A days. I wouldn't say today because there's a lot I got to catch up on. Yeah. Okay. Yes, Friday the 16th. Second. Okay. I'll meet down in your office. Okay. All right. Bye-bye. Cool. Sorry. That was a phone call. I was the one in trouble. There we go. So I posted this worksheet into the Google Classroom. For those of you that are online, for those of you that are here, obviously you got this thing in front of you. So let me just show you this real quick. Kind of go through this little brute force method that we've talked about. Here we go. The brute force algorithm. Step one, make a list of all possible Hamilton circuits for the graph, which we did. For each Hamilton circuit, calculate its total weight. Now, they say weight because they don't know if these numbers are measured in money, distance, time. They don't know. And if you don't know, then they just call it a total weight in general. Then it says to choose an optimal circuit. Optimal circuits always come in pairs. Oh, we saw that. A circuit and its mirror image, so that there will always be at least two optimal solutions. Then they have exercise one. Exercise one, we just did. We just did this one. This is the exact example that we just did. They say a traveling salesman lives in town A and must visit clients in his hometown and 3 other towns. Distances are given in miles. Okay, so they did miles. I did minutes, whatever. How many possible Hamilton circuits, including mirror image circuits, are there in this problem? Now, even though we checked 6 of them, there are technically 24. Well, actually, no. There are 24 if you consider you can start from any town. There are 24 if you can start from any town. But it says that he lives in town A. It says that he lives in town A. Now, this is part of the real life issue. The real life issue is that you can't start in any town you want. You can't. Because this man lives in town A, there are 6 possible circuits that he can take. The answer would be 24 if you could start anywhere. But there are 6 that he can go on because he has to start in town A. It says use the table to determine the optimal route. Well, we did that. Let's see. A, B, C, D, A. A, B, D, C, A. And A, C, B, D, A. These are the only 3 that I have to list. These are the only 3 that I have to list. And the reason for that is because the remaining 3 are nothing more than mirror images. They are the reverse order. And in fact, they want that on the side right here. Mirror image circuit. Well, the mirror image, ADCBA, just taking it backwards. ACDBA and ADBCA. Those are the mirror images. What are the optimal routes? Well, we know what the optimal routes are, and it's 115. It's basically the one on the top left and the one on the top right. Oh, these things. Let's see what I got here real quick. Now, I am not going to finish this one today, but I would like to take a look at exercise 3. We're not going to be able to finish this one today, but I would like to take a look at exercise 3. And if you notice, for exercise 3, instead of forcing you to list them all out, for exercise 3, they listed them out for you, which is very nice. Let me just see right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 24 routes that you could take starting at E. There are 24 routes that you could take starting at E. There's 12 on the left, 12 on the right. Now, yes, they're mirror images of each other, but that's what's going to happen. You'll always get the mirror image in one sense or another. A delivery truck starts from the warehouse at point E and must deliver packages to 4 locations. Okay. Travel times to delivery locations are given in minutes. So instead of miles, this is time now. This is time. They want to minimize the amount of time that they spend driving on the road. How many possible circuits, including mirror images, are there in this problem? Well, I just said 24. And there are in this problem because you have to start from E. In fact, if you could start anywhere you wanted, there would be 1, 2, 3, 4. There would be 4 times as many. So what would that be? So 96. Gosh, I would never want to list out 96 possible routes. I never would. Although I probably have in the past. But this is basically what we'd have to go about doing. Now, brute force. Pro, if you used strategy 1, brute force, you'll get the optimal route. Cool. Con, brute force sometimes takes forever. Sometimes it takes a long stinking time to do brute force. Ugh, goodness gracious. Let me just do a few of them, see how long they take me. Let me see here. So if I'm going to go on this route right here, it would start in E, and then I would go A, B, C, D, E. Okay, so I would go, let me get a calculator here. I know I could do it in my head. I just don't want to mess it up. 40 plus 15 plus 14 plus 13 plus 22. That would be 104. That would be 104. And of course, the mirror image would be the same thing. Now, if I change it up for the second one, it would go E to A, which is 40, to B, which is 15, now to D, which would be 11, then to C, which would be 13, back to E, which is 23. All of a sudden, I get 102. I get 102. Goodness gracious. Like I said, sometimes it does take forever. It's a little tedious at times. Now, in the coming class periods, I am going, yes, brute force will be one of them, but I also have 3 other strategies that I am going to show you. 3 other strategies that I'm going to show you in regards to Hamilton paths and circuits. It's going to be nice. Eventually, this is going to culminate in a project. Ultimately, this is going to culminate in a project in which you are going to pick certain destinations around the country. And you are going to have to look up the travel time, or the travel mileage, I should say, between these wonderful destinations. And you are going to figure out optimal routes for traveling the country. You might think, have you ever seen like these like maps on like, I don't know, Twitter or whatever, where they show like, here's an optimal route for traveling the country. It's like just one big loop, some junk like that. No? I've seen them. I don't know. But traveling the country in just one big loop is not always the optimal route. It's not. For example, right here, I just went around E, A, B, C, D, E, and it took 104. But then if you cut a few corners in between and actually switch up a couple of destinations, you get a total distance of 102. Or actually time in minutes. Time is money. Time is money. On Wednesday, we're going to finish up this exercise. I'm going to show you how to use the table at the bottom. And then we'll see what the next strategy has in store for us. For those of you in the chat, oh, Hawaii, here she comes. Nice. She says, does this project involve us buying plane tickets and taking this route? That's completely up to you, Sydney. That is completely up to you. I am not going to force anyone to do that. But if you want to, you can. That'd be great. Although you can't use Hawaii for the project because you can't drive there. Sorry. Anyway, if you haven't left a comment in the chat, please make sure that you do so. And we will pick up with more of this on Wednesday. It's going to be nice. Anyway, the bell's going to ring in approximately less than 20 seconds. So I'm going to leave the chat open for a few more moments just to give those people an opportunity. What is going on with this thing? Oh, did this all dry out? Oh, that would be silly if it dried out. Anyway, there's the bell. All right, there, yeah, I almost got it. All right, I'm gonna sign off. See you. There we go.